Good morning, everybody. So with all the video bombing going on, that's why I've required the password, and I've got to keep my eyes open. I have to admit everybody into the meeting. So there's someone else, Jennifer. I have to admit people one at a time. So I have to keep my eyes open for that as we get started here. People are joining. A couple announcements to make. Can everybody hear me? Just double check. Someone give me a response, either chat or audio. Okay, good. Thank you. All right. So I do have a couple announcements to make before we get started. We have a decent amount to do. So first, where's my list? First is people are asking about their grade because the pass-fail is out. The pass-fail option is out, and so a lot of people ask me about their grade. And a couple things. One is, obviously, if you're an A or B student, you're going to be choosing the grade option. If you're a D or F student, you're going to be choosing the pass-fail option. It's really only a choice for C students, in my opinion. As far as your grade goes, the syllabus hasn't really changed. We've changed how the points are coming about a little bit in terms of quizzes instead of clickers, things like that, but the syllabus is still the same. One thing to remember that is that D2L doesn't recognize the fact that some of those clicker/quiz points are bonus points. And when you look at the syllabus, we're only counting 100, meaning if you get 110, you're getting 110 out of 120. I'm not sure what you see on D2L exactly. I have all different views. I can see points, percentages, everything. But just keep in mind that you have over 100% then on your clicker points, and D2L might report that as, 110 out of 120, whatever that comes out to be, 90 something percent. So the easiest thing to do is just add up all your points and then divide by the total, using the total from the syllabus, realizing that the clickers, there's bonus points in there. So after your quiz Thursday, all of the clicker quiz points will be in. And when you divide, just remember when you add your denominator that the quiz clicker should only be 100, not 120. Other than that, it's really up to you whether you go with the pass or fail option. So if you have any questions, just email me about your grade, but I think that has pretty much stayed intact. I will tell you that with lab, there's probably going to be a change, and you should be getting an email this week. It looks like we're probably going to do away with the lab final. It hasn't been decided yet, so don't cheer too much. But I think we're just going to do another lab on electrochemistry next week. Believe it or not, next week is the last full week. You were supposed to have your lab final on Tuesday, obviously. Not Tuesday, Tuesday for my group, like Brittany and Andrew. But you were supposed to have your lab final next week. I think we're just going to do another lab on electrochemistry. And what I'll do is, regardless of what's decided point-wise, I'll scale everything up to the 160, so my syllabus stays the same. So if you wind up getting, 90 out of 100 points, whatever we wind up total with, then I'll just take that and multiply it by 160. So that will stay the same, because I know a lot of people depend on a lab grade to kind of boost their grade up. So I want to keep that point total the same. I'm not sure if Dr. Phelps is going to have a pre-lab or not, because we are missing one pre-lab also. So we'll either wind up with probably either 95 or 100 points instead of the 160, because I believe the lab final, or maybe, is that right? Oh, yeah. So we're missing a lab too, because we lost a week. So I think what we're going to do is still drop your lowest, but we're going to replace it with your highest. And that'll be good, because most people at least have 110. So you'll still have, you'll wind up with either 95 or 100, depending on whether she comes up with a pre-lab or not. And then I'll just multiply that to get you to 160. The other thing I want to tell you, I know that some people have missed the last exam, and some of this remote stuff is causing some problems. So as a result, I'm giving a makeup exam. But what this is going to be is something like I've done in the past. I don't like the idea of only giving the makeup to students that had trouble Since spring break, some people had legitimate reasons for missing an exam before spring break, death in the family or something like that. So what I'm doing is I'm giving what's called a cumulative makeup, because it's going to cover anybody that missed any exam. I'm not making up 5 different makeups. What I do is I give this on study day. I'm allowed to do that because it's optional. It's not required. You can't give anything required on study day or reading day, whatever you call it. You'll get information on this, but basically it will be cumulative for 11/20. Anyone that missed exam. I know that Logan missed an exam. I thought I saw his name as a participant, but I'm not sure if he's here or not. I'm not sure, but I know David also missed it. So I'm going to give a cumulative makeup on study day. It'll cover all of 11/20 material. Anyone can take it, even if you didn't miss an exam. So if you happen to miss one exam, you get to drop that, but maybe you have a missed exam and a really poor score, and you want to take it. But it is cumulative, so most people are not going to bother taking it if you have good grades. And the way I'll treat it, basically, you guys will wind up with 5 hourlies, a makeup, and of course, your final exam can replace any score. So you'll actually wind up with 7 exam scores. I will drop your 3 lowest. That's the way it will work. So if you don't take the optional makeup, it'll be a 0 and be dropped. It's the easiest way to do it on D2L. I just put all 7 grades in, and 5 hourlies, an optional makeup, and your final exam will go in twice. It'll go in as a final exam and as an hourly, and then I will drop your 3 lowest. So just be on the lookout for that. I'll put the announcement on D2L. It'll be done the same way. It'll be a D2L document. It'll just occur Thursday morning on reading day at 8 o'clock for anybody that's missed an exam. All right, so be on the lookout for an announcement from your lab instructor. Be on the lookout for announcement about that makeup exam, and also think about your decision about pass or fail grade. With that, I had a couple emails of people that wanted to spend some time asking questions about the exam. I don't even see the 2 people that asked me to do that here. Let's see, there's someone's coming in, Daniel. Katrina was one. So I'm not sure if she's here or not. But anyway, I'm not going to go over the whole exam. I'm going to flip through, and if you have questions, you have the key and you have the responses. If I don't get any questions, I'm going to move on. We have a decent amount of material to do. Yeah, Katrina is here. Oh, there she is. Yeah, she's here. She's one of them, and I forget who the other one was. So I'm going to share my screen. It's going to have the exam on it, and I might pick out a couple I thought were difficult, but please chat in, raise your hand. The raise your hand feature moved. I think it's now under, it's where it's under participants. I think I can't see it because I'm the host. It used to be under chat, and they got a couple new versions that have come out on Zoom. So, all right, I'm gonna share my screen, show you the exam, and then just say, you can just type the number of the one you want me to go over into chat, and I'll go over it. All right, let's see, share. All right, let's see if we can make this a little bit bigger. And then, all right. It's under participants. Yeah, thank you, Dawn. They moved it there from chat. It used to be under chat, I believe. So if you are looking for the raise a hand feature, otherwise you can just type a number into chat, and I'll stop on that one. I am going to go over the first one because it's not as maybe easy as it looks or straightforward as it looks. I think everything else on the first page I thought was pretty straightforward, but someone might have a question. So I'm going to talk about number 1 real quick. Correct answer for number 1 is E. K is much greater than 1. The process reactants come to equilibrium rapidly. You might think to yourself, well, equilibrium constant doesn't say anything about rates. Well, it does actually. The one way to define the equilibrium constant is the forward rate constant over the reverse rate constant. That's why when I told you guys to make sure you understand the equilibrium constant in all its definitions, that is the correct answer, because that means the forward rate constant is much larger than the reverse rate constant. So, so what are the other choices though? When K equals 1, the forward and reverse rate constants are equal. Wait, what am I looking for here? Yeah. What the heck is with this? Identify the choice, the best complete statement to answer your question. Which of the following statements are going to equal? Oh, it's not true. Right. Sorry. Not true. Because D is true, right? K equals 1, the concentration of products and reactants at equilibrium are equal. That is true. K much less than 1, the concentration of reactants is much greater than the concentration of products. Yes. And NA is true. Concentration of products much greater. What's wrong with E then? K is much greater than 1. Products and reactants come to equilibrium quickly. No, so I misspoke. So K is defined by rate constants, but it doesn't tell you how fast it comes to equilibrium. It just means where your equilibrium lies. It's the same as the previous questions. Because the forward rate constant is much greater than the reverse rate constant, your equilibrium will lie further to the right, but it doesn't tell you how quickly things come, because that depends on rates, not rate constants. So I misspoke there. See, I tricked myself too, sorry. All right, so got to read it though. It says, which is not true. That's the only one. I was confused about number 3. Okay, that's fine, Katrina. I know it would be very similar to how the original. I just thought the whole thing was squared. I was just wondering where I confused myself. Okay, let's take a look at number 3. 3 is for the chemical equilibrium. Okay, a value of equilibrium constant case 10 was the value. Okay, so yes. So it is squared. You're correct. So if you square 10, you get 100. So the correct answer for 3 is D. So when you think about this, you have products over the reactants. It's going to be C over A times B. And then once you put 2's in front of that, it's going to be C squared over A squared times B squared, which is basically equivalent to just squaring that whole thing. It's the same as this. C squared over A squared times B squared. So effectively your K will need to be squared. 10 squared is 100. So that's where D is coming in. I wrote it up there too, but we're talking about 3 right here is 100. So 3 is in fact D. Does that help, Katrina? Okay, Katrina? All right. Yes, thank you. Okay, great. So anybody else with anything else on page 1 here? You will need to know the stuff for the final, obviously. I'm gonna close my door here. Hang on. All right, let's move to the next page. And questions here. So I will talk about 10 here, and I will actually talk about 11 also. But any questions on 6, 7, 8, or 9? Okay, 10, you can use the shorthand approach too. So 0.5 molars much greater than the Ka here. So we use that shorthand notation. And if what you remember, this is, let's see, what is this? This is as a weak base. Okay, OH negative. So X is going to wind up equaling OH negative in your Rice table. And that's simply the square root of the initial concentration times the Ka or Kb. So basically it'll be 0.5 times 5.7 times 10 to the minus 10. You don't have to do the Rice table. You go straight to the shorthand because we had said that if the initial concentration of the acid or base that you're dealing with is greater than 100 times the Ka or Kb, you can use the shorthand Rice table. Just remember, X is now your hydroxide concentration. So you take the negative log of that and then do your pH, POH thing, and you should get, oh, I'm sorry, it's not asking for pH. It's just asking for the Ke. What are we asking for here? Concentration of OH negative. So you don't need to do anything. Just solve for X and didn't ask for pH, sorry. Just solve for X and that's your answer. You don't have to worry about doing the negative log or anything. So you can use the shorthand notation there. And no more questions on, if there's no questions on that, I'll move on to 11, which I thought was the most difficult mathematical one on the exam. I did not give you a quadratic. You can thank me for that one. And you definitely won't see one on a final exam. Just takes a little bit too much time. So for 11, for this one here, your Rice table here will look like this. And I wish I had a little more room, but maybe I'll write it here. Br2 plus Cl2 goes to your Rice table is going to be 0.5, 0.5, 0, minus x, plus 2x, right? And then I got to let some participants in. Sorry. Oh, wow. We got a bunch of people I'm missing here. Connor just joined us. There's Logan. All right. Sorry, guys. Connor and Logan. I've got to pay attention to the part. I got to let you guys in manually. Logan, just to update you, missed this. So hopefully you can hear me. There will be an option to take a makeup. Just keep your eyes posted to email and to D2L. It will be a cumulative makeup that anyone can take that missed any exam during the semester, and it'll occur on reading day, because I know you had asked me about that. So just keep your eyes and ears peeled for that. We're going over the exam right now. We're on number 11. We're not doing the whole thing. So looking at your Rice table then you're going to wind up with 0.5 minus x for my equilibrium, 0.5 minus x, and 2x. Putting that into your expression, you're going to wind up with your K equal to 2x. You've got to square that over 0.5 minus x squared, and that equals your K, which is given to us, 7.2. Now, the easy way to solve this, take the square root of both sides. You don't need to do a quadratic. Take the square root of both sides. You get rid of the squares. You wind up with the square root of 7.2. Then it's easy to just cross multiply, combine your x terms, and solve. And for 11, you will get E. And of course, you guys have the correct answers, and you have the key, and you also have your D2L answers. So that is 11, which I thought was mathematically the more difficult one on the exam. Any other questions on this page? So 12 through 17, please. Yeah, sure. Let's take a look at 17. The first disinfectant used by Joseph Lister was called carbolic acid. This is now phenol. pKa is given. The pH, we want to know what the pH is. So once again, we can use our shorthand notation. Remember, pKa is just the negative log of the Ka. So that means my Ka is actually 10 to the negative 9.9. And the same shorthand that I just used a second ago, we can use again, because the initial concentration of the acid is equal to 0.1, which is much greater than that Ka. It needs to be, you know, at least 100 times greater, we said, but it's obviously way much greater. That's almost 10 to the minus 10, and we're at 10 to the minus 1. You're looking at about 9 orders of magnitude here. So we can use the shorthand again. Let me let some more participants in. We can use the shorthand notation again. And once again, we can say that X, in this case, is going to equal, since we're dealing with an acid, X is going to actually equal to the H positive, which is going to be the square root of the initial concentration of the acid times the Ka. That is the shorthand notation, because we are satisfying the fact that remember your rice table, that X is going to wind up being small enough that we can take it away from the, your denominator winds up being 0.1 minus X, basically, when you do your rice table. X is going to be super small, so we assume that the denominator is just 0.1, and so everything reduces to this. So now you just plug in 0.1 times 10 to the negative 9.9, square root of that. That will equal X. That's your hydronium ion concentration. And we're asked for the pH, so then you take your negative log of that. And for 17, we get D. Okay, for that page. Okay, Dawn wants me to do 14. Okay, so these are pKa values. So the lower the pKa, the stronger the acid, because remember, it's just the negative log of the Ka. So 10 to the negative 1.23 is greater than 10 to the negative 3.4, right? So 10 to the negative 2.3, or OA, is the stronger acid. We were asked to arrange these decreasing acid strength. So we want OA to be first, and following that reasoning, C is the correct answer. So the smaller the pKa, the stronger the acid. Other questions before I go on to the next page? Because we do need to get you guys ready for the quiz and hit electrochemistry. So your last quiz is Thursday, and it will, I'll show you exactly what it'll include up to. It's going to include up to basically reduction potentials and being able to read a reduction potential table. That's going to be the majority of your quiz. I think 6 of the 8 questions are on that. All right, so we got 18 through 24 here. Questions here. Okay, going once, 20. Let's do 20. Kirlos wants to do 20. The aqueous solutions of blank are basic. So once again, this is one of those ones that gives people some issues. It's had to determine whether a salt is acidic or basic. And if you remember the chemistry, it's basically what the ions are going to do in solution that determines whether the solution is acidic or basic. And I said a good shorthand kind of trick to figuring that out. Just pretend like these are acids and bases combining. So if I take something like E, effectively, if I combine KOH and HI, that's a strong base and a strong acid. That's going to be a neutral salt, okay? Realizing what's happening in solution is that both K plus and I negative are too weak to do anything. So they're not going to act like acids or bases. That's really what's happening chemistry-wise. So for one to be basic, what we're looking for is basically a cation from a strong base and an anion from a weak acid. And there's your one that should jump out at you is A for 20, because potassium hydroxide is a strong base. HF is the one halogen that's a weak acid. So that means what happens in solution is F negative reacts with water to form HF plus OH minus. That's actually what's happening chemistry-wise. So that's going to be a base. It's acting like a base, right? It's producing hydroxide. Remember the definitions? Base is a proton acceptor, electron donor, hydroxide generator. So there it is, acting like a base. So that solution will be basic and 20 will be A. Other questions on this page? Okay, let's scroll to the last page. I think there's only 2 questions. Either of these for anybody. In fact, 26 is kind of explaining the very one we just talked about. It's NAF rather than KF. But the explanation is right there, because the answer to 26 is B. Fluoride is a weak base, and that's exactly why. Okay, a couple people said 25. Both Daniel and Jace. So this is about stalactites, stalactites, and stalagmites. I always forget which one's which. I think they're the ones that are on the ground. The ones formed from the ceiling are the stalactites, I think. Anyway, I digress. All right, the Ksp of calcium carbonate is given. What's the concentration of the saturated calcium carbonate solution? So this one is one of actually a little bit more straightforward of a Ksp. Some of the Ksp ones can be really tricky, but this one really is just the Ksp is equal to 4.5 times 10 to the minus 9, and just write your equilibrium expression. Products over reactants. These are always written as solid on the left, like this. So basically, this is equal to the concentration of calcium ions times the concentration of carbonate ions. So basically what we have is 4.5 times 10 to the minus 9 is equal to x squared. These are both going to be x. They're both going to be the same concentration because they derive from this. So the concentration of calcium has to be the same as the concentration of carbonate. You solve for x, that's it. Take the square root of 4.5 times 10 to the minus 9, and that is your answer. And for 25, that winds up being C. And that's really all there is to that one. You guys are probably kicking yourself. It's just a square root of the Ksp. That is your solubility. Some people have trouble making that connection. I think that's probably where the problem is. You know, you don't realize that that is the solubility of the salt, whatever, you know, one of these is. Now, if you had something like this, this would be X and this would be 2X. The solubility of the salt is X, not 2X, because this is a one-to-one relationship with this, and this is the solubility of the salt. We're talking about the salt. You'll wind up with twice as many chloride ions in solution. That's because of the formula of the compound. There's 2 chlorides for every 1 calcium, and there's 2 chlorides for every 1 calcium chloride. But the solubility will be, in this case, X, and not the 2X. So that's one of the keys to some of these that are not one-to-one salts. Other questions about the exam before we move on to electrochemistry? All right, so your quiz is made up and should be, you know, visible, not the actual quiz questions. It should be visible on D2L. Of course, that'll be Thursday morning at 8 o'clock, so we won't start our Zoom session until 8:30 Thursday. You'll be getting an email on that. And I'm going to take you through some of the early electrochemistry. Actually, first I want to review what is in Chapter 8 that you need to know for both your quiz and for just diving into this chapter. And that is oxidation reduction and redox. So real quickly, reduction is loss of electrons. There are other definitions. I said that wrong. Gain of electrons. Why did I say that? Oxidation is loss of electrons. There are other definitions, but that one is the most universal that applies to everything because there are oxidation reduction reactions that do not involve oxygen, do not involve hydrogen. The other definitions include those. You might say to yourself, that's kind of odd definition. Reduction is gain of electrons. Well, what we're talking about is the oxidation number is reduced. So, for instance, this is zinc picking up 2 electrons. The oxidation number here is simply the charge 2. Over here, any element has an oxidation number of 0. Basically, just means it's kind of a fancy name for the charge. And the reason we call it oxidation number is because in some cases there's not a charge. So for instance, there's no charge on these, but they have oxidation numbers. And it really is kind of like the theoretical charge within the molecule when you assign the electrons to the more electronegative element. So we've got to remember the rules for assigning oxidation numbers. So let me jump back up here real quick. Metals, elemental metals, you're always going to look for them to be oxidized. That's what happens. They get attacked by oxygen and other substances, and they lose electrons. You've never seen me in 2 semesters of chemistry, for those of you who had me for 2 semesters, ever write anything like this. A metal with a negative charge, okay? Just doesn't happen. They all lose their electrons. So metals are always getting oxidized. So like copper solid will go to copper +1. It can go to +2 also, +1 electron. It loses an electron. Just think about this like algebra. 0 equals +1 plus a -1, right? That's all it is. It's just an equation that algebraically is summing up those charges. So the charges have to be equal on both sides, and they're 0 on both sides. So when you think about oxidation numbers, there's some rules. And the rules are the oxidation number is just the charge if it's an ion. Oxidation number for the chloride ion is -1. If it's an element, it's 0. So hydrogen gas, oxidation number there is 0. Anything in its elemental state. Any compound now, the individual atoms will have oxidation numbers because we're going to assign the electrons to the more electronegative elements. So the rules are basically hydrogen's for you guys going to be +1. There's some cases it's -1, but don't worry about that for now. You'll get that later in advanced chemistry, but basically it's +1. Oxygen's for most cases is going to be -2. And you go back to chapter 8, you'll see these rules. Fluorine's -1. A lot of times your halogens will be -1, but they can take on other charges. Fluorine's the one that's always going to be pretty much -1. That's because it's the most electronegative element. So it doesn't matter what it binds with, it's going to steal the electrons. That's why we assign it that -1. It's always going to be that. So when you follow those rules, that's really about it. I hope I'm not forgetting anything. Oh, your group 1 and group 2 metals are going to be +1 and +2 in a compound. So when you have something like sodium chloride, okay, we all know that this is +1 and this is -1. Those are the oxidation numbers. In ionic compounds, they tend to be more real charges, but there's plenty of salts, metals, and non-metals that are not true ionic compounds, and they become more polar covalent compounds than they are ionic. So oxidation number is a little bit more appropriate. So when you look at something like CH4, how do you assign the oxidation number to carbon? Well, there's no rule for carbon, but there is a rule for hydrogen. So you say you got 4 hydrogens and oops, what did I just do? I have no idea what I just did. Somehow shorten the page here. The heck? Oh.
If you hit the little, like the looking glass thing with the plus sign, that'll go away.
Thank you. That was a new one to me. All right. So, whoever that was, thank you. I didn't see who that was talking to me, but anyway, thank you. Okay, so we're trying to figure out the oxidation number on carbon and CH4. The rule basically is hydrogens plus 1. So that means I have 4 hydrogens. I have 4 hydrogens all at plus 1. I have a plus 4. The compound is neutral. There's no charge on this compound, so it's 0. If there was a charge there, we'd have a charge written there. So that means carbon has to be minus 4. You see that? Does everybody see that? The carbon's going to be minus 4 because each hydrogen's plus 1 based on our rules, and the compound is 0. So it kind of looks like this. The total charge is equal to the hydrogen plus the carbon in this particular case, and the hydrogen's plus 1, and there's 4 of them, and the total charge is 0, so you solve for what carbon is. That's all we did, really, and therefore carbon is minus 4. So that's how you assign oxidation numbers. That becomes important because when you see a chemical reaction, you have to be able to figure out what's being oxidized and what's being reduced, and I'll do that on the next page. But before I do that, questions about general definitions of oxidation reduction and how we go about assigning oxidation numbers. And I will do some more examples of oxidation numbers over the next couple minutes, but let me make sure there's no questions right now. Okay, so let's take a look at the oxidation number on something like this. Oxidation numbers. So the question now is, what are the oxidation numbers on the atoms? And that would be sulfur and oxygen. Okay, so the rule says that oxygen is minus 2. So I'm going to do this and say, okay, well, my total charge is 2 minus 2. That's equal to the charge, that T stands for total, by the way, on sulfur plus the charges on oxygen. Well, oxygen's minus 2, and there's 4 of them. So we now have minus 8 plus what equals minus 2? And of course, the answer should be plus 6. Right? That shouldn't be super surprising to you because, do I have? I'm sorry, I was looking for a periodic table. Shouldn't be super surprising to you because sulfur is in group 6 or 16. So effectively, going back to Gen Chem 1, it lost all 6 of its valence electrons. And in this case, it's plus 6. Why? Because it's bound to a more electronegative element, oxygen. Questions? Okay, so let's look at a chemical reaction then. All right. Am I balanced? Yes, I'm balanced. Okay, let's look at a chemical reaction. So now questions are, what's being oxidized? What's being reduced? What's the oxidizing agent? What's the reducing agent? And how many electrons are being transferred? So when you look at this, you say to yourself, oxidation number here of oxygen element is 0. In a compound, it's -2. So I'm doing oxygen now, specifically, is -2. So oxygen clearly has been reduced. It's gone from 0 to -2. Right? And whatever is reduced is the oxidizing agent. It's carrying out the oxidation. Basically, it's stealing electrons, so it's being reduced. So O2 actually is the correct oxidizing agent. O2 is the oxidizing. O2 is a classic oxidizing agent. You know, attacks a lot of things, metals and all sorts of organic compounds. It will oxidize. So therefore, something's being reduced. Well, carbon over here. Now, hydrogen is +1 everywhere because it's just in a compound. So nothing's changed there. So hydrogen everywhere, if you will, is +1. Nothing's happening there. So the obvious thing is that carbon then is what's being oxidized, right?
Excuse me.
Yes.
Okay, so I was having a really difficult time when I was reviewing oxidation reactions and balancing the reactions. And one problem was giving me a difficult time because there was an oxygen in every single compound in the reaction, and they were all different. They all had different oxidation numbers, and I did not know how to handle that.
Yeah, don't concern yourself with the real advanced ones, but oxygen only has two, really is either -2 or -1. And I'm not holding you responsible for anything other than -2. It is -1 in peroxides, okay? And I doubt that was in your book. So oxygen might, other than 0, of course. Yeah, go ahead.
It was a HO2 minus plus MnO4 minus produces MnO2 and O2.
HO2 minus?
Right.
Okay. Yeah. What number in the book is this?
It's the practice. It's in chapter 8.6. It was when I was reviewing.
Okay.
And it was.
I'll look at it. Yeah, I'll look at it, but don't concern yourself with that one, okay?
Okay. I could not balance it for the life of me. I was having the hardest time.
Yeah, and don't worry about balancing. Yeah, because so that is that the chapter that goes into it, or is it this chapter? There's one. I don't think it's this chapter. Where you have to balance. Acid-base oxidation reduction reactions, and you have to add waters, and you have to add hydroxides.
Right.
Yeah, don't worry about those. You don't have to balance those. I don't even cover that in normal situations, let alone this.
Oh, okay,
Yeah.
okay.
Yeah, there's all those acid-base ones that you have to balance, and I didn't even cover it in Gen Chem 1. But I'll look at that because that doesn't look right to me, OH2 minus. But I have to see what the reaction looks like.
It was HO2 minus.
Oh, HO2 minus. Like, oh, okay. This?
Yeah.
HO2 minus.
Yes.
Okay. That makes more sense, yeah. Yeah, but don't worry about those. So in that case, yeah, that's a case where exactly what I told you. It's a peroxide, so that is oxygen's -1 there, and hydrogen's +1. So you got 2 -1s and a +1. Your total charge is -1. That makes more sense, yeah. Yeah, but don't concern yourself with those. So what's happening here then is carbon on the right, we'll leave carbon as red here. Carbon on the left, I'm sorry, not on the right, is going to be -4, kind of what we saw before. Is that the same thing we did before in methane? Yes. So it's -4. And on the right, it's +4 because of 2 oxygens. 2 oxygens, each -2. That makes it +4. Effectively, that means we have 8 electrons being transferred because we go from -4 to +4. So we needed 4 to go from -4 to 0. We need another 4 to go from 0 to +4. So 8 electrons have been stolen from the one carbon, and they've been distributed to the 4 oxygens, each of them going from 0 to -2. And since there's 4 oxygens, each one gets 2 electrons. That's your 8 electrons. The number of electrons has to balance. That has to balance. Otherwise, there's something wrong with your stoichiometry, obviously. That's kind of what Connor was getting at with balancing the acid-base reaction ones, but those can be really difficult. So does everybody see what we did here? So effectively, that means that carbon is oxidized. And if you will, CH4 is the reducing agent. The actual atom that's, oxidized is carbon. So carbon's the atom, if you will, but most people think of the agent as the compound that you would add to your system that would reduce something. So we think of methane being the reducing agent and oxygen gas being the oxidizing agent. Questions on that? Oxidation reduction can be a bit challenging. Okay, so then we need to jump into electrochemistry and get you ready for your quiz. And I'll tell you exactly, same format, I'll tell you exactly what to expect. All right, so this is the chapter. Learning goals, all that. I'm not going through all of this because we don't have the time for it, and this is all just basic stuff, and you have your video. It's just reading your learning goals, reviewing this. Definitions of electrochemistry. It's your half reactions here. Here we go. Let me turn this the other way. It's a little bit better, I think, this way. All right. Here you see some of these half reactions. Electrons always have to equal out when you write the overall reaction. So if this had been something like copper 1 plus 1 electron going to copper plus, you would need to multiply that second reaction by 2 before you add them up to get your overall reaction. Okay, so in the case here, the zinc's being oxidized and the copper's being reduced. And it basically comes down to affinity for electrons. When you bring 2 substances together, one will have a greater affinity for electrons than another. And that's what causes the oxidation reduction, because these are both metals. And one's being oxidized, one's being reduced. Of course, the copper is not an elemental metal, it's copper 2 plus. If we had elemental copper, well, that would be a problem. We wouldn't have a reaction because you're not going to form copper -1 or -2. You wouldn't have a reaction if I put zinc solid in a beaker with copper solid and water. Here what we got is zinc solid, which is the strip that you're looking at, in a copper probably sulfate solution, because that's that pretty blue color. That's copper sulfate. It's my favorite inorganic compound. Do you have a favorite inorganic compound? I love that color, so that is my favorite compound. You see it in crystal form. It's just this beautiful turquoise blue. So we have to have that copper ions there because they can now accept those electrons. So the zinc is being oxidized, the copper ions are being reduced. The zinc, therefore, the zinc solid is the reducing agent. The copper ions are the oxidizing agent. And we have 2 electrons being transferred. But if for some reason this was just copper 1 and you wanted to add these up and get the overall reaction, you would have to multiply this by 2 because the electrons have to cancel out. So just keep that in mind as you go through the chapter and they ask you things like, how many electrons are being transferred, or write the overall reaction. You often have to do that. Stop me with any questions at any time. One thing you need to memorize is the anode is where oxidation takes place. Now, electrochemical cell. These types here, let's see, is this word introduced yet? Okay, so these types of cells here that generate energy, like a battery, these are galvanic or also voltaic. They're the same thing, just two different names. They're types of electrochemical cells. The other type at the end of the chapter is the electrolytic cell. Those are the ones where the reactions are not spontaneous and you're using electricity to drive the reaction. These we're getting energy out of. That's why we make batteries out of them. Okay, so this could form a battery here. This is a spontaneous reaction that gives you a voltage. That's what you see here. And oxidation is going to occur at the anode. So you see here, and the anode's always going to be negative charged in these cells. When you get to electrolytic cells, which we'll talk about on Thursday if we get there, if not on, might not be till Tuesday actually. Your exam's a week from Thursday. And all your materials are available, outline all that. So in these galvanic voltaic cells, the anodes are always negatively charged, and oxidation is taking place there. So to form an electrochemical cell, we still have two metals here to form our electrodes, but we got to have that copper solution there because the copper is what's being reduced. And the zinc solution is fine, but we're going to be forming more zinc ions. And you always have to have a connection for these ions to migrate through, because if not, the system will shut down. There'll be a collection of charge. It has to migrate and maintain what's called electro neutrality. So we're going to actually have to have, zinc ions moving in that direction to replace the copper ions that are being plated out onto that copper cathode to maintain electro neutrality. And then things like the sulfate ions, maybe if these are sulfate salts, say that's copper sulfate, then the sulfate will have to move in that direction. Wait, I got that backwards. No, wait, let's see. So we're losing, the copper ions. So zinc ions have to be replaced, and that's fine. And the negative ions are free to move in either direction. So sulfate ions. So as the zinc ions move in this direction, you'll have an excess of negative ions. So the sulfate ions also have to move in this direction. So you have to maintain that electro neutrality. And they've got sodium ions in there. So basically, this is like a sodium sulfate solution here. It's not a zinc solution. They're using sodium sulfate, I guess, there. Doesn't matter. You can use anything. It doesn't have to be the exact same metal as what's the electrode's made of. So you can just use any salt solution there. So this is the way we notate this. And there's a quiz question on this. So what we do is this represents the phase boundary. That's this right here, the salt bridge, okay? And this represents, that represents, that's the salt bridge. These are the phase boundaries. Okay, the single lines. And my notation on the quiz is a little bit funky because there wasn't a single line. The double line I had fine. I had to use like capital letter, the capital letter I or something to get that to work. So if it looks a little funky, just ignore that on the quiz. But so the way you write it is you write it in kind of the anode on the left in the direction of which the reaction is happening. So zinc is converting to zinc 2 plus, okay? Copper ions are converting to copper solid, okay? That's the way you write it with the anode on the left, okay? And if there are, lots of times they leave out the 1 molar if it's just 1 molar, But if there's other concentrations, then you need to include those in there because that does affect your cell. And you'll see that as you move on in the chapter. But that is how we notate it. So you should be able to take a notation like this and write what the reaction is, or you should be able to take a reaction and write the notation. Either way is fair game. Questions? So the quiz, you've got one question on oxidation numbers, one question on this right here, and the rest of the quiz is what we'll be getting to in a bit here. I don't think I need to talk about this. So this is just a standard cell, and I'll show you that in a table. Basically, we pair up species with the hydrogen electrode to get standard reduction potentials. So this is just another cell diagram here. These are Voltaic cells. Here's an example of one where we were asked to write the reaction, write the diagram here from the description of the reaction. And since the oxidation is going to be on the left, we got the magnesium go to magnesium ions. We got our salt bridge, and then we have copper ions being reduced. So that's the way you write that one. So standard potentials, the potential of reduction half reaction in which all reactants and products are in their standard states at 25 degrees C. We call this voltage, if you will, the electron motive force, and we tabulate these values. And this is basically a key equation for you. And this is the equation that allows you to figure out what the E naught of a given cell is, which in this case is effectively, where's the one with the meter? I guess there isn't one with a meter yet. I was looking for one with a meter rather than a light bulb. A meter rather than a light bulb. But I guess they're coming up. So this is going to allow you to calculate what the, there it is, what the E of the cell is. And what this is, it's like a potential energy. It's almost like calculating how much potential energy is from the top of the waterfall to the bottom of the waterfall. It's the difference in the affinity of the electrons measured as a potential for that energy. Okay? So what we do is we tabulate all these values. Excuse me. What you see here, this is a tabulated value that was measured against a standard hydrogen electrode. I'll show you the table in a second. And this is the zinc value measured against the standard hydrogen electrode. What we simply do is we plug the values direct from the table that you'll eventually see, right, like this. These are all reduction potentials. Every one of these reactions is written as a reduction. So it's the potential for the species to be reduced. This is the potential for fluoride to be reduced to the fluoride ion. And has a large positive number, and it's at the top of the chart, which means it has a very high potential to be reduced. Should make sense to you. Fluorine, right, is very reactive. It's in group 7, right? It's kind of electron hungry, if you will. It likes to form the fluoride ion. So it is one of the more readily reducible species. When you get down to something at the bottom, like lithium, well, that's the lithium ion. It's not the lithium metal. It's the lithium ion, and it will be reduced to lithium solid, but it's not particularly favorable by the large negative number and the low position on the chart, because you know that group 1 metals tend to like to, right, lose an electron, not gain. So they like to be in that form of +1. So as a result, lithium ions are not particularly prone to be reduced, but fluorine gas is particularly prone to being reduced. So what you simply do is you take those numbers straight from the chart and you plug them in here. You don't switch them around. What's happening is, since they're both reduction potentials, we cannot have a reaction like this. These are both being reduced. In order to make a working cell, one of these is going to have to be oxidized and one is going to have to be reduced. So in building a cell here, we're going to have the elements here, right? How do we decide which one becomes oxidized, which one becomes reduced? Well, the one with the higher reduction potential is the one more likely to be reduced, which is this one. That means to make a working cell, the other one has to be oxidized. So effectively, what we're realizing is now, and this is the same reaction we've been working with, is to make a working cell, that's the silver one. The zinc, heck, is it this far back? The zinc is being oxidized and the copper is going to have to be reduced. So effectively, what this equation does for you is switch the sign of the anode. And the anode is where the oxidation is taking place. So what that's saying is, well, this reaction is not happening. I know this is a lot, trust me. The reverse of the reaction is what we want. We want zinc being oxidized. We're going to reverse it just like you would reverse an enthalpy or a delta G. You have to reverse your free energy. I'm sorry, free energy. Your reduction potential. And the equation does that for you by having a negative sign there. So all you do is pull the values straight from the chart and put them into this equation. And since these are E's, that means they're reduction potentials. There are some people that will do it slightly different, but this is the way I recommend. Just pull the reduction potential numbers off the chart, put it in here, and you get your value, which is this right here. That also tells you what the reaction is, because effectively you would be flipping this reaction, and zinc would be going to zinc 2 plus 2 electrons. That would be oxidized. The copper would be reduced. That's a heck of a lot. So questions? No questions. So either you're numb or I'm just awesome at explaining this stuff. All right, so let's move on then to the table, because that's what you're gonna need to understand for the rest of the quiz. So one thing to realize, it is an intensive property. If you remember that back from Gen Chem 1, probably very first chapter, does not depend on the amount that's there. Okay, just like the density of lead is the density of lead. It doesn't matter whether I have a gram or a kilogram, the density is the same. It's the same with reduction potentials. Use my waterfall example. It doesn't matter how much water is coming over. That's not what I'm calculating. I'm calculating the potential energy, which is the height of the water. Yes, the amount of water will come into play later when we're looking at how much work we can do, which basically is delta G. But for right now, we're really looking at the potential difference between two species and their affinity for electrons. That's all I'm interested in, is the affinity for electrons. It has nothing to do with the quantity of material. In this case, copper has a greater affinity for electrons than zinc. And that's measurable by the characteristics of the element. We're not talking about the amount of material. Here's where it says, the work does depend on the quantity also. And remember, that's what we use for work. We defined it that way. Define G as the amount of work that's done, remember? And we said H is that kind of that total energy that's available. But now we're gonna relate G to E rather than H. So very simple equation that you'll be given on your next exam, of course. But N is just a number of moles. Faraday constant is a constant that's been on your constant sheet all semester, and it will be there again. And the E of the cell is what we just calculated up here. So you can, and these numbers are straight from the chart, you can either calculate G if you know E, or you can calculate E if you know G. Either way is reasonable. So it's kind of, you know, your volts here is what we're looking at. This is just simple practice you can look at. It's solved for you. I went over it. It's in the slides, and I think it's in the video. This is what I was talking about before. That slide kind of showed this, but this is the one that really talks about it. This is our standard electrode. It will serve as either an anode or a cathode. What you're going to do is pair this up with any species you're interested in measuring its reduction potential. We had to come up with some standard. This is what we do all the time. We compare everything to this. That's how we generate the table. On the left, we used it with zinc. On the right, we used it with copper, and effectively we define it a value of 0. That's all we do to get a table like this. And there is your standard electrode right there. I'm going to erase some of this stuff now. There is your standard electrode right there. So when you pair it with anything above it, the ones above it proceed as a reduction, and you have positive values. If you pair it with anything below it, that would need to proceed as an oxidation, and the standard hydrogen electrode would proceed as the reduction. So if I pair it with fluorine gas, the fluorine gas will proceed as a reduction, and the hydrogen gas now will be oxidized, and this will move in the opposite direction. If I pair it with nickel, the nickel, the standard will proceed in the reduction direction, and the nickel will proceed in the oxidation direction. Carlos, I'm not sure what your statement there, second option, meant. I don't know if that's a question or not, but maybe it was something we were talking about back here. But so when you look at a table like this, as I said before, this is going to be a list of reduction potentials. And a couple things we need to talk about here is, what's the strongest oxidizing agent on this table? Does anybody want to venture a guess? And you can just type it, or you can say it. Nobody be so bold. All right. What's the strongest oxidizing agent? Well, another way to write that question or word that question, what's the species most likely to be reduced? Because remember, the oxidizing agent is reduced. Will be F2. You want something at the top of the table on the left, because that's a reduction, and that's 4. That means F2 is a really strong oxidizing agent. So is oxygen. Oxygen is not on this table, surprisingly. I forget where I got this table from. I guess it is from your book. Maybe it's an older one, though. But anyway, F2 is the answer to that question. That's the strongest oxidizing agent. You can also reword that question to say, what species on this table is most likely to be reduced? The answer is the same, F2. Okay? You should recognize that question either way, okay? That's valid either way. Now, does anybody want to venture to tell me what the strongest reducing agent is on this table? Very good. Lithium. Andrew says lithium. Notice he didn't say lithium plus, he just said lithium. It's going to be exactly the opposite. The bottom right. Another way of wording that, strongest reducing agent is the substance most likely to be oxidized, which is the lithium element, not the lithium ion, right? you would have to oxidize lithium plus to +2, which is certainly possible. Oh, for crying out loud. Which is certainly possible, but not likely. So it's not going to be a particularly good reducing agent, lithium +1. So those are the answers to those two questions. Now, the other thing I want to ask you is which pairs work, if you will. And to answer this, what I mean by that is, will fluorine gas oxidize silver metal? So here's the silver metal right there. There's fluorine gas. Will fluorine gas oxidize silver metal? Yes or no? No one? So the way to answer these questions, okay, Andrew said no. So the question is, will fluorine gas oxidize silver metal? The way to answer these is, if the one above has to be on the left and the one below has to be on the right to be correct. So the answer actually is yes, because this is the more preferable one to be reduced. So it will proceed as a reduction. If I pair it with silver, so let's say we have fluorine gas, fluoride ion in solution, we got silver metal, and we got silver ions in solution. Will this reaction happen? Will fluorine gas oxidize silver metal? The answer is yes, because this will proceed as the reduction. It's the one higher up. This will have to proceed as an oxidation, so the answer is no. I mean, so the answer is yes. So if I had said, will fluorine gas oxidize silver ion? Well, we don't even have that's not a pair that's going to work. We don't have a reaction for silver ion going to silver 2+ anyway. So you always want to look for the top one being on the left and the bottom one being on the right. So if I said to you, will bromine gas oxidize manganese 2+ ion? The answer needs to be no. Okay? Because the bromine's down lower. So the magnesium 2+ is not going to proceed in the opposite direction. And that's what the question's asking. So as long as you pair them up so that the top left reacts with the bottom right, which means fluorine will basically oxidize anything over here, because it will pursue a reduction if I pair up with any of those. And another way to word these is to say, hey, will aluminum solid reduce chlorine gas? Will aluminum solid reduce chlorine gas? Again, yes, chlorine gas will be reduced. If I had said, will aluminum solid oxidize chlorine gas? Well, that would be chlorine gas going to chlorine plus, and that would be no. I mean, there's not even a reaction like that on the table. We don't have that tabulated, but that's just not going to happen. So what you have to realize is the one down below on the right proceeds as the oxidation, and this proceeds as the reduction. So be careful of the wording and be careful of the pair and looking at the pair. Questions? That pretty much prepares you for the quiz. 6 questions from the 8 on the quiz are from a table you're given. It's the same table in every question, and it's questions like this. One is a cell notation, with this. And one is, hey, what's the oxidation number on blank in this compound? Any questions about anything? Those that joined late, I did talk about you know, deciding between pass and fail. And I talked about having a cumulative makeup exam that anyone can take that will occur on reading day. And it can do that because it's optional. It's not required. It will replace any exam you missed. And I also talked about lab. You should be looking out for an email from your lab instructor. We may be doing away with the lab final. Any other questions or comments? I'm going to stop my share here. And obviously you're free to go anytime anyway, but of course, I'll stick around if anybody has any questions. Otherwise, I'll end the meeting. Any last minute questions? I will see you on Thursday after the quiz. Good luck on your quiz. All right, ending the meeting.